In 2013, the Safire project was created. The objective was to replicate the Sun's atmosphere in a laboratory on Earth.
Wow, look at that.
A lab was designed and built, and at its heart was the Safire plasma engine, the only one of its kind on the planet.
Michael, if you guys want to turn your microphone on at any time.
Okay, we can see you and Colin. Can you see me in the background talking to you on the cell?
Today, 4 years later, the Safire team gives a tour of the lab via the web to a scientific review panel scattered all over
today,
North America. Two things define Safire: a unique premise and a remarkably powerful methodology. The premise driving the project is the idea that electricity plays an essential role in the functioning of the Sun's atmosphere. The methodology used to build and run the Safire lab comes from the world of engineering and manufacturing. It is a statistical procedure that allows for incredibly precise control over the design and managing of experiments. This combination of premise and methodology has yielded remarkable, if not startling, results.
Comment that those last 2.58s, how would you for?
It was 0.5, I thought.
No, 7 and 8.
The actual position of the plasmas here. Yeah, so this is Safcon. So this test, we have ongoing video feed of plasma. And I think we're increasing the current now. Yeah. So these cups that you see, these balls, are actually not sitting on the surface. They're actually sitting just off the surface.
In August of 2017, the Safire team presented its most recent discoveries at the Electric Universe Conference, Future Science, in Phoenix, Arizona.
Just listening to Safire, and that's just the beginning.
Wow, that was the Safire.
So Safire has proven itself to be capable to contain, control, and stabilize high-energy, dense plasmas, and you're going to see that tonight. We're seeing chemistry changes. We are slowing the speed of light down. We're seeing variations in electron density comparable to the photosphere, heliosphere, and nuclear bombs. Electrical confinement of high-energy photons. These are just some of the things. And all of these things here are due to charged plasma affecting matter of a different electrical potential. So this time, I want to take the opportunity, which is usually saved until the end of the presentation because time is short, to thank the other very key members who are contributing so much to the success of this endeavor. So first of all, I'd like to thank Scott and Bruce Mainwaring for their ongoing and unwavering financial and moral support. Dr. James Ryder for your insight, for an ear to hear, and with help herding the cats. And Dr. Lowell Morgan for your amazing knowledge and insight into the complexities of plasma physics. Walt Thornhill for your work in the electric universe model and cosmology. And Dr. Don Scott for your work in developing a more mature model of the electric sun. Jan Andercho for your hard work in data acquisition. Leighton McMillan for your hard work and the assistance in building Safire in such a short time. Jason Lickford for your work in mechanical engineering and telemetry. I'd like to thank you, Susan Sherratt, for your untiring help in administration, finance, and legal matters, helping to make this project go so much smoother. Tracy Childs for your ongoing financial work and for always being an awesome woman in my life. Ben Gedlow for your work and the team in pulling this presentation together. And none of this would have started without you, David Talbot, making that providential call to persuade me to take on this project. So now I would like to introduce part of our team who are joining me tonight to assist in presenting our discoveries. Please welcome Dr. Michael Claridge and Dr. Paul Anderson. Research objectives. There's a lot of detail to it, but fundamentally,
you're welcome.
Safire stands for Stellar Atmospheric Function and Regulation. The objective sounds way out there, but basically the contract says we're to do everything we can to recreate a star in a jar and test the electric universe and test the electric sun model.
I actually haven't had a chance to see this
So the technology we're going to use in
myself, so
Safire,
like,
or have been using in Safire.
I'm watching it with you. I mean, you
We have floating potential, plasma density, current density, electron energy distribution, electron temperature, mass spectroscopy, optical spectroscopy, thermal measurements, infrared thermography, radio frequency measurements, electromagnetic measurements, scanning.
I better shut up. Since I'm going to watch it, I might as well see whoever else wants to watch it is hanging around or whatever. So, what's up?
Part of our team who are joining me tonight to assist in presenting our discoveries. Please welcome Dr. Michael Claridge and Dr. Paul Anderson.
But this is, Kevin, how you doing? Yeah, you know how it goes. Sometimes people will try to argue like, oh, really? You can't really hear me? Well, people try to argue like, oh, this is pseudoscience and blah, blah, blah. And it's like, actually, it's experimental physics, and they don't want to hear it. And then, those people, they don't seem to ever show up when we're actually showing this physical data, in these experiments. And they just, you know how it goes. But, let me see if my recording device is turned up right. There it goes. Alright, so yeah, I don't really want to talk too much over this anyway. I just wanted to point that out. It's pretty sad. It's, their names are like, whatever. This is YouTube handles and shit, and we're talking about these guys that they're talking about and shunning are like, doctor this and professor that, and it's like, come on. Not that I'm saying for an appeal to authority, but they actually have appealed to authority issues, and they still, assume that I must be talking about, some random Kirby vacuum cleaner salesman who makes YouTube content or something, and how it's got to be just bullshit. But yeah, I'm excited to see this. I'm gonna go ahead and hit play.
Research objectives. There's a lot of detail to it, but fundamentally, Safire stands for Stellar Atmospheric Function and Regulation. The objective sounds way out there, but basically the contract says we're to do everything we can to recreate a star in a jar and test the electric universe and test the electric sun model. So the technology we're going to use in Safire, or have been using in Safire, we have floating potential, plasma density, ion current density, electron energy distribution, electron temperature, mass spectroscopy, optical spectroscopy, thermal measurements, infrared thermography, radio frequency measurements, electromagnetic measurements, scanning, electron microscopy, optical microscopy, voltage across the plasma, current across the plasma, voltage feeding the plasma, current feeding the plasma, and video capture of the plasma phenomena. And we're going to discuss each one of these with you in detail tonight.
He's like ran out of breath talking about the list of equipment that goes on the data measurements you're taking.
Just kidding. What we will show you, however, is how we use this technology to reveal some of the most startling discoveries we made this year instead. Now, Michael, you're up.
I'm up.
Let's get started.
Optical spectroscopy. So Jim Ryder said everything we know is from light. I'll think about that. But almost everything we know about the sun is definitely from light. And optical spectroscopy is a really good friend as a scientist. Every element emits very characteristic frequencies. A lot, you could imagine, like every species of bird has its own song, and you would never confuse a chickadee with a seagull, right? So if you study these elements spectrographically, each one is quite unique. And we can learn a lot about what's going on for those atoms by things like the relative heights of those spectral lines, the widths of those spectral lines, the shape of those spectral lines. Here's 3 different discharge regimes in our plasma. On the left, you can see there's the center anode, very bright, and then around it is a halo. Okay, those are our double layers, a halo around that. In the middle panel, you can see that the double layer is gone, right? Just the center anode is there. And on the right-hand panel, we basically just cranked all the dials up to 11 and got a super high power discharge. You can see there, that's our spectrographic probe tip. It's a fiber optic that we can move around anywhere we want in the chamber to study what's going on. And so right there, that fiber optic tip is looking right into the double layer. Okay, it's not looking at the anode, it's looking at the double layer. The next one, the double layer is gone, so the probe tip is just looking at the general plasma discharge. And then the last one, we move the probe, but it's looking at this super high power discharge. So we'll just look at one spectrographic line. This is like one note being emitted by the hydrogen. Okay, it's the 656 nanometer line, one of the most famous spectrographic lines in the universe. And we can measure the width of that. And inside the double layer, we see the width is 0.012 nanometers. Okay, that's pretty tiny. These are pretty good instruments we have. We boosted the resolution spectrographically by about a factor of 4 or 5 just recently, so 4. It's good, right? That's pretty good resolution. Then the double layer goes away. The width of that line, same line, hydrogen emissions, the width goes down to 0.07 nanometers. And then for the third one, the super high power one, it jumps back up to 0.09. This made us super excited to be able to see this and measure this, because one of the reasons these lines can change their shape like this and get broader and more narrow is the number of free electrons running around in the plasma. Okay? And if there's a lot of free electrons running around the plasma, you can kind of picture that they're crashing into hydrogen atoms and causing extra wobbles on top of the note that's being emitted. That tends to broaden the line more. Okay? That may seem like a small change, 0.05 nanometers from 12 to 0.07, but that represents like 50 to 100 times change in the free electron density. So double layers have within them about 100 times more free electrons running around than not, okay? This is super exciting that we can measure this. If you just stick in a probe into one place and you get one measurement, you're not necessarily so sure you can guarantee what you're looking at. But if you can measure changes like this, then you have much more confidence as a scientist that you're actually observing something that you can talk about. And where do we see comparable changes, in free electron density? Well, we see those changes going from the photosphere to the chromosphere, from the chromosphere to the corona, out at the end of the heliopause. So we're actually getting into the realm where we have changing conditions in our chamber and the ability to measure them that are also going on in our star. That summarizes that. I think it's too early to stop. Do you think it's too early? I think it's too early to stop.
I think they're just absorbing right now.
Yeah.
Right.
So we'll just take a breath and keep going?
Sure, you can take a breath. I'll keep going.
Okay.
It's not always this much fun in the lab. There's a lot more yelling and screaming going on and things like this. So the next section is where we get into the fun part, statistics, okay? But it's really, really important because design of experiments actually is the mainstay. It's the foundation of the work that we're doing. Because in science today, there's a lot of stuff that's in question, and we're not going to be subject to those kinds of questions. So we impose what's called design of experiments, and Dr. Paul Anderson is going to take you through what we've been doing with Safire. And I think you're going to be amazed about some of the findings we've done.
All right. Thank you, Monty. So just as Monty said, we wanted to investigate some basic plasma physics that is occurring in our chamber. The first thing we did was, in looking at our chamber, was that we wanted to tame the plasma. Okay. Now I'm going to show you first a video here of the plasma as we know it now. We can move the cathodes, as you can see. We can stabilize double layers. We can change the double layers as a function of distance. At the same time, we can also change gas concentration and type of gas in there. It wasn't always that pretty. Some of our initial plasmas were pretty dirty, very unstable. If you look at a lot of old plasma literature before they even named it a plasma, they commented on how difficult it was to contain this energy and understand it. So these are some of our initial discharges, lots of impurities on some of the materials that we use for the anode, striking different discharges, a lot of instabilities in the plasma. And what we eventually wanted to look like this, right? This is a very simple plasma, which entails a simple anode on the left and a cathode on the right. And this is basically a 1D plasma where you're striking a discharge between these two electrodes. You can adjust the gas pressure, the gas type in this, as well as the voltage in this system. Fairly straightforward. This is a top view of Safire. It's not as straightforward as the plasma tube. This is looking down on Safire from Monty's model here. And as Monty listed in previously, all the instruments that we have them there for a reason. And in every single run, we use all the control instrumentation for the chamber, as well as driving all the detection that Monty mentioned. So there's a number of detectors on here, as well as the fundamental control of the chamber. So through a lot of data acquisition and controlling, we're able to now control that plasma chamber and carry out experiments. So one of the first things we had to confront is how to drive it and understanding the gas input. Like, this is just one aspect of the gas input here. This is the gas and vacuum control system. We also had to understand our
running around the plasma. You can kind of picture that they're crashing into hydro 4 or 5
plasma as and SOPs to implement safety procedures when you're working with 2,000 liters of hydrogen at high temperature, right? So we had a number of things to control in addition to wanting to control the plasma. So we looked in the literature and we talked about it and we said, okay, well, learning to drive this, let's concentrate on plasma experiments that are well documented. And that's why we came up with Paschen's Law. We decided to choose Paschen's Law to understand the plasma ignition in the Safire apparatus. So Paschen's Law describes a point of current flow at a particular electric potential through an ionizable gas or gas between two electrodes. Okay? So fundamentally, we have two electrodes, positive and negative. You have a gas. You have a certain pressure of that gas, usually conducted under vacuum. And you have a distance between those electrodes. And you strike a voltage. And there's no current flow initially until you get to a certain point where that voltage can overcome ionized gas and conduct a current. Now, when that occurs is a certain voltage. Okay? So we decided to do that in Safire. So this is a classic passion curve in hydrogen. The other gases also have other curves that are very similar. They exhibit the same minimum. So if you notice here in the graph, our x-axis here being a term of PD, pressure and distance. Notice it's in a logarithmic scale. So it's a reduced variable, so you have both pressure and distance in one axis. And in our y-axis, we have our voltage that we strike to obtain a discharge. So if you go ahead and do a bunch of plots at different pressures, at different distances, you'll end up falling on a curve like this for your electrodes. So what we did in Safire, we went ahead and did in Safire apparatus with a spherical anode and our two cathodes at various distances, equidistant. As much as we wanted to vary both of them, we kept them constant. And we discovered already Safire is acting very differently than a typical plasma discharge apparatus. We had to use a modified version of Paschen's curve, which you see there, of the law. And we also found that the gamma term, which is in that lower denominator in the denominator, that did adjust with different distances. And so that's something new that we're exploring, and we hope to get a publication out of this. So you'll notice that already we have a departure from regular plasma physics in a regular anode cathode discharge and, say, a discharge tube. And another reason why we did this is, okay, we ignited the plasma, but what is the morphology of the plasma? What does it look like at these various settings? So it was kind of an experiment with killing two birds with one stone, in that we determined the ignition characteristics which we needed to control the plasma, and we also explored the morphology of the plasma, right? So that was a very powerful thing. We were able to pursue some various regimes and then establish our design of experiments. So we discovered that the configuration is a significant departure from typical plasma apparatus that you may have from a typical anode and cathode. So then we went into the design of experiments. We decided on where we're going to look, what kind of plasma regimes we want, because ultimately we want to dial in stability for experiments. There's no use in doing experiments for double layers if they appear for 1 microsecond and then go away. We wanted them nice and stable. Now, to obtain stability in any system, whether it's in Safire or whether it's in your kitchen baking bread, we need reproducible results, but that only comes from understanding your factors. Factors is another word for variables. So to understand those factors and variables, you need more experiments, right? Traditionally, this is called the Edisonian approach. You have more factors, you do more experiments, you get more data. The problem with that is that just because you do more experiments, you might not be increasing the resolution. In other words, the signal to noise. The signal to noise that you're looking for. You need to increase that signal from the noise so you get reproducible results and you know you're stable. And what design of experiments does, it's a methodology. It increases the resolution, but it also decreases the number of experiments you have to do. So I urge many of you who are experimentalists or who are curious to look up design of experiments and to learn the techniques, because it is extremely valuable in both saving time and resources, and it greatly increases your resolution. Now again, I won't go into why that is. I discussed a little bit of it in my past presentation, and you can read about it online. But basically what you're doing is you're conducting experiments where you're making sure your points are orthogonal. So in other words, two factors are always opposite each other, and you're making things symmetric in your design space. Just an example of what that does for you, on the right column here, you can see the efficiency. That's a measure of the experimental variance. You can actually calculate the variance in your experiment prior to even doing experiments with your design. Now, OFAT stands for one factor at a time. That's how traditional experimentation is done. That's how the Edisonian approach is done.
Hey, what's up, my friend Calic and I here. In a moment, I'm going to step into my office here at my home and pull out my computer.
That's how the Edisonian approach is done. And so you can see here it's comparison between a traditional number of runs, where you're kind of a shotgun approach to experimentation, and what's called a full factorial DOE. There are many types of DOEs out there, but this is just the most basic taught DOE. And you can see that just with 3 factors, right, say pressure, type of gas, and distance of the cathodes, right? That's 3 factors, 3 variables. With the number of runs for OFAT, you need 16 runs. That gives you a certain experimental variance or efficiency of 2. But you're half that number of runs with your full factorial DOE. And as you get upwards, now you still say, wow, well, 128 runs, that's still a lot of runs. But there are as I said, there are other DOE formulations that you can pursue to help with this, to help decrease that number more and still maintain that experimental efficiency without having to do 512 experiments. So in a nutshell, that's really what DOE is. We explored this first in phase 1. This is our phase 1 setup. Very simple. We had an anode in a bell jar surrounded by a cathode. We had a voltmeter. Did have some other instrumentation crammed in there. But for the purposes of this was just a snapshot of one of the bell jar experiments with a small anode. And really what we determined through design of experiments is these various regimes that the plasma goes through. So we were already kind of dialing in the anode, even in a small bell jar, so logic would assume we could do that when we scale up as well. And actually it does when you use the right approach, when you use designs of experiments. So we were really happy with our various regimes. This is a snapshot of, I would say, the main regimes we work with. That's not to say that there aren't others in between there. So I'll just go through here a little bit and show you close up. I call this a dark quiescent phase. This is right on the edge. Very small changes here. This is not stable. Very small changes in either voltage or current can lead to this extinguishing. But there is still a plasma layer around the edge of the anode. Now, as we increase our current, we obtain what we call tufts. These are anode tufts. These have been experimentally seen before, but we can now control them. We can control the number, the concentration in a square area, and they're always equidistant from each other. Okay? And as you increase the energy and as you increase the current in the system, they start to grow in size and also squeeze together until you reach a point where they actually start to coalesce. And this is what we refer to as moving tufts, right? This can also be adjusted in terms of pressure and current. So as these things start to move, they actually spin more, and eventually what comes into being is this double layer phase. Multiple double layers that are controlled by current and gas pressure. So this was probably the most double layers we obtained, I would say, with a 3-inch anode. This is a 3-inch anode. This is a 3-inch anode, so those tufts, I think we reached up to about 7 or 8 tufts, at least in the design of experiments that we got.
Yeah, they're about this big.
So, and they're stable. And also we have quiescent phase. This looks familiar, doesn't it? We even got some holes in that arising from something. We don't know. All right? And that layer is fairly significant. It stands off the surface of the anode. And we also have these asymmetric double layers that occur over time. Time is also a factor, but we weren't able to quantify it yet. Because what happens over time is your anode heats up. Thermionic emission happens. It changes the properties. So that's the one factor that we have to dial in a little bit more, is we don't understand the effect of time on this anode yet, but we know it affects it. And also, the ZAPM high intensity kind of let it loose phase. So those are stable regimes. All right. So to dial in the plasma also, we wanted to work with different anodes, different size anodes. The top is a 1.5 centimeter anode. The bottom is a 3-inch anode. And you'll notice that we're obtaining the same regimes. A little bit different shapes, but for the most part, we're getting the same numbers and at proportionally the same current. And what do I mean by proportionally? Well, when you're impinging a 1.5 centimeter or inch anode compared to a 3-inch anode, the current density is a lot higher on that, right? So we had to adjust our current density properly to obtain the same response. So that's what we did in this experiment. And these are just some numbers if you want to have fun with the numbers. We're calculating, but we're getting about 85 watts per square centimeter in the top discharge. But you can see in the bottom one where we throw in 22 amps, we're getting a little bit less wattage there with the calculation, but within error, you're almost there. So we're tracking very well with scalability of the plasma between different sizes. And as you can see, the current is the main driver. That's what has to be adjusted. Now, we say here, you may say indications of a transformer. Well, that's the only way, that's why we have in quotes, right? Transformer. So as double layers form, plasma resistance decreases and current flow is less impeded. Michael alluded to that earlier. Electrons are more intense or more concentrated in these double layers. Why is that? We'll have to study some more. But now is where we get into our statistics. What you see on the graph, this is an actual by predicted plot. This is what comes out of design of experiments, okay? It may just look like a straight line to you, but this is very powerful because what it enables you to do is to predict things, okay? So the top graph here has, as you can see on the y-axis or the vertical axis, okay? Thank you. On the vertical axis, you have voltage actual. So that's the voltage we actually measure. And what do you see here? Voltage predicted. Okay. So when you read papers, scientific papers or any kind of reports that have prediction values, that's what they're referring to. They're building a model and they're seeing how well the model can predict the voltage or whatever response they're studying. So we can look here that the equation of the line is pretty darn good considering the fact that we're working with a plasma. Okay. It's an R squared. I go by the R squared value is about 92.92. You look at the error, it's only plus or minus 10 volts in that prediction. Okay. We had a number of responses or a number of observations in this set of experiments, 31 experiments. Okay. So we have sufficient degrees of freedom when we're only